WhatsApp, you can access it through that. First of all, I would like to give a basic introduction to what the project idea is. Here you are seeing the input data of this research paper actually, and it is a continuous time series data of strain versus time. The strain is the magnitude of expansion that we are measuring for the gravitational waves. Now, what are gravitational waves? So we are trying to measure the gravitational waves using something called a Michelson's interferometer, and I will show you the design of it. So this whole project is based on identifying gravitational waves using instruments like this. Of course, they are much bigger than this, 4 kilometers in size. And what we are trying to measure is the phase difference between two lasers that we identify here at this detector, and that we infer as the strain. Now we run this interferometers over runs like 6 months, 9 months, and we have lots and lots of data about that. How do we process this data is kind of a part of this pre-processing step. So this is what the data looks like before pre-processing. Now let's take a look at different data processing methods that we have. Now if you just simply look at the raw data, this is what it would look like. It does not make any sense. But once you start doing different transformations on it, the actual data is the orange part on the given background noise, that is the blue data. So all of this blue data is created by different sorts of noise from instruments, from earthquakes, from vibrations, everything. Now we have to understand how accurate this model has to be, because this is the most accurate measurement that we have taken in the history of humanity. We are looking at strain data that is accurate up to the size of 1,000 of a diameter of a proton. So you can imagine how much precision is required. And to remove this background noise data, one way is to use machine learning algorithms. And we will soon look at how we can do that. First, let's take a look at how we transform the data using different methods. Okay, so also this is another example of when we actually detect a gravitational wave. So even the background noise is changing with the input data. So it's not something that when we get the input we can directly extract it. And let me just show you the main part of the process. So first of all, we fit the input data that is in time series format to a statistical tool called Omicron. What Omicron does is it identifies the whole, it transforms the whole data into cube plane, and in cube plane we have our frequency domain, that is FFT is done. We have frequency domain, we have time series, and we also have energy. So what we are looking at is the SNR graph of the input data. Now you notice the spike in the middle. It could be due to both input signal and also some noise parameter. And how do we resolve that is, first of all, we'll expand in terms of the time domain, and then you can see this is clearly a noise. Now let's take a look at an actual gravitational wave detection. So first of all, you are not able to see anything unusual, right? All the small specks are just background noise. Now once we keep on running the Omicron, that is trying to identify these time periods where the actual input is, you'll start noticing a trend here, which was not visible earlier in the SNR value. And as soon as we magnify enough, we can see this particular wave. So this, what we are looking at, actually is the collision of two black holes far deep into space, way beyond the reach of electromagnetic spectrum. So we cannot see it, but using gravitational waves we can identify. And during that detection, there was a high noise due to error in one of the instruments. So this is this noise transient is caused due to the detector's error. So how do we differentiate between both of them? One way is of course identifying the SNR value. Noise transients always are very short-lived and have very high SNR values. But statistical approach can only take you so far. So let's deep dive into how machine learning can help us better identify these noise transients. And just let this image be here for a while. So in this paper we are employing random forest and another method called KaruGP. KaruGP is a genetic programming algorithm much similar to the human genetics and how the whole process of mutation, reproduction and different generations work. and we'll take a look at each of them. So first of all, we are using the standard scikit-learn library to employ the random forest. We have done the hypertuning. I mean, the scientists that have worked on this have done the hyperparameter tuning and identified 500 number of decision trees to be ideal for the data set that is O1 and O2 runs of the LIGO detector. And next we are trying to verify the results that we get from this random forest output using CargoGP. Now what we are doing here is classifying the different auxiliary channels. Auxiliary channels are readings from all the other sensors apart from the main sensor that we are using. And what they are defining is temperature sensors, vibration sensors, sound sensors, everything that you can imagine. And what we are trying to do is classify them, classify them based on the amount of changes that they cause in the main channel. So although one of the vibration sensor might be affecting a lot or might be vibrating a lot, it is not necessary that it applies to the main channel. So the main aim of this whole research is to classify the auxiliary channels into those having the highest effect to the main strain channel. And as you can see in the result section, each type of sensors, that is physical environment sensor, temperature sensor, whatever, has different RF importance. Yes? So okay, I will conclude by saying that CargoGP is an amazing program that uses very low computational cost, and in this study we found that CargoGP is way more faster than RF and computationally inexpensive while giving the same accuracy. Now feel free to ask questions while I do a test run of CargoGP. Anyone has questions? So anyone has questions?
Figure 3 equation.
Figure 3. Figure 3 gives you a good example of how genetic program is generally used to solve arithmetic operators. So they are giving you an example of, say, if you want to solve A multiplied by B divided by B multiplied by C. So how you can use genetic programming to do that. And as you can see, there are two different nodes there. There is the parent node, that is the main operator, and then there is the child node, that is created by the mutations of the parent node. And it does not actually apply to this study, but it's an example to understand how different operations are done using genetic. Any other questions?
Can you tell more about CargoGP, because what kind of algorithm is it?
CargoGP is entirely based on, okay, so it has loaded. So CargoGP is entirely based on genetic programming. Genetic programming is, as I mentioned, very similar to human genetics, where the idea is to mimic human anatomy and the whole process of cell division, cell reproduction, and the iterations over it. So what CargoGP does, is not visible. So if you can see here, you have multiple options in CargoGP specifically to select. For example, if you want to create a full structure, a RAM structure, we'll just look at a simple structure for now. Create default 3 number of trees, each tree has 3 depth. There are minimum number of 3 trees, and by default let's take and let's take 2 generations. So how many epochs are there per iteration? And then we have multiple options. Let's just quickly move to this one. So as you can see, when I press enter, it runs through different iterations of the genetic program. And what we saw here is actually the prediction values based on one of the data set that it has. Similar to the iris data set that you might have worked with. And so the benefit of RGB is that it is entirely written in C++ and it is very computationally efficient because it gives you, and also it is very easy to recognize errors because it gives you output on every single step. So you can just stop the model at any step and identify the outputs and then return. So that's the reason that it was used in this study to verify the results of random forest. And as you can see here, you get the information of different trees. Any other questions?